Hello, hello everyone. Hello, Toby.
Hello.
There's two of you. So which one should I make the host?
The one that's not speaking, the one that's just
One,
blank.
the one that's blank. Okay, perfect. All right. So speakers. Lovely. Okay. And mm, make host. Perfect.
Okay.
So we should see some more people joining. I've just sent a reminder to everyone, and
Okay.
yeah. Okay. Then off to you. This is the second to last webinar. So next week is going to be the final webinar for year 13 this year.
Oh, okay.
So yes. So yeah. So you have the closing act.
Yeah, so I've got
Right.
this week and next week.
Yeah. All right.
Both thermodynamics. Okay,
Okay. To you then.
I'll get started then. That's quite a long sheet. Okay. This, yes, there we go. So just to start off with just kind of some definitions and things. So the first one is whenever we talk about temperature, we use absolute temperature. And this means that zero, and this is measured in Kelvin. And what this means is 0 Kelvin is absolute zero. So that is where kind of atoms stop moving, everything has its lowest possible energy, all the vibrations and things going on, they all stop. So 0 Kelvin is absolute zero. And really, the only difference between this and Celsius is that 0 Kelvin equals minus 273.15 Celsius. The differences are the same. So something changes by 1 degree, it changes by 1 Kelvin. The only difference is where the zero is. So you just have to add or subtract 273. The other thing is heat. Now, in kind of ordinary life, we're kind of very used to thinking of heat and temperature as the same thing. But in physics, they are different. So heat is energy that's flowing. So it's energy in transit. And this is different from the energy an object has. So I've just made a cup of tea. There's energy coming out of this, and I feel that as heat. So I can feel that energy, and I'm feeling the heat coming out of it. And that's caused by it being hotter, but temperature is to do with and we'll see this later, temperature is to do with the energy in the mug, but heat is the energy coming out. So they're very easy to get mixed up. But heat is about energy moving. And finally, the specific heat capacity is the amount of heat. Remember, heat was energy G needed to change temperature of 1 kilogram by 1 Kelvin. And the equation for this is the amount of heat needed, and for some reason, heat is always given as a Q. This is equal to the specific heat capacity times M times the change in temperature. So here is heat, specific heat capacity. This is the mass, and the change in temperature. So this tells us the more we heat up a material, the more we want to change the temperature of a material, the more energy we need to put in, which makes sense. And the last thing is the specific heat capacity depends on the properties of the material. So water has a really high specific heat capacity, which means you need a lot of energy to change the temperature, whereas metals have got a low specific heat capacity. So you don't need much energy to change the temperature. Okay. Have a look at this first question. Hopefully these ideas, there's quite a few there. Hopefully they'll become easier as we see some examples. So a car is traveling at a certain speed. It brakes. How much heat does the braking process create? So it initially has kinetic energy. And we're going to say all of this goes to thermal energy. So in other words, the thermal energy we end up with is the same as the kinetic energy we started with. So the heat is a half mv squared, which is equal to a half times 1,000 kilograms times 27 meters per second squared, which is equal to 364,500 joules. There's an energy, it's measured in joules. Okay. In the winter, people find they get hungrier as the body needs to get through more food so that to replace the energy you need to expend to warm your body up. So if you eat a Mars bar, how much can the body warm itself up with the energy provided? So we want to look at the change in temperature from the energy in a Mars bar. So the energy is going to all be converted to heat. So we have Q equals energy from Mars bar we want delta T, which is the change, how much warmer your body can get. So let's have a look. Let's use this equation. So we have Q equals Cm delta T, which gives us the change in our body temperature is equal to the energy from the Mars bar divided by the heat capacity and the mass. So our bodies, they're pretty much entirely made of water. So we're just going to use the heat capacity of water, which is 4,200 kelvins per joule. That should also say per kilogram in there. So, and then the mass, well, I haven't given you the mass in this question, but let's just estimate it. I've given you quite round numbers. A person is maybe 70 kilograms, I think is average for an adult. But somewhere of that order is fine. So the change in temperature is equal to 1 megajoule. So that's 10 to the 6 joules, which is all the chemical energy in the Mars bar, which will all go into heat, divided by the mass of a person times the specific heat capacity. And you put this into your calculator and you get 3 Kelvin. So if you had a Mars bar, your body can warm itself up by 3 Kelvin. That's assuming there's no, you're not losing heat, which obviously you are because it's a cold day, you're losing heat, you have to move, you have to think, you have to pump blood around. So obviously not all of the energy won't go into heat. But if it did, you could raise your temperature by 3 Kelvin. Okay. So you go exploring on a hot day and you find a nice rock on the floor and you want to keep it, but it's really hot, so you can't put it in your pocket. So you put it in your water bottle to cool it down. The water bottle has 600 ml of water and it's initially at 4 degrees. What is the final temperature of both of them? So if you put the rock in the water, they're going to end up at the same temperature. And if there's no heat loss from, if it's a well-insulated kind of flask, then no heat's going to be lost, and all the heat that leaves the rock is going to end up in the water. So all heat leaving the rock goes into the water. Okay, and we'll call the final temperature T final. So heat lost from rock heat lost is mass of the rock times the specific heat capacity of the rock, which we see is given to us, times the change in temperature. So it started off at temperature T rock and ends at T final. And similarly, heat gained by the water is equal to the mass of the water times the heat capacity of the water. And now we got to be careful with the signs here. Here I started with, we're looking at the rock, I started with the temperature of the rock and I took away the temperature, or the final temperature of the rock. For water, we need it the other way around. So in both cases, so the reason is, in one case, we're looking at heat leaving. In other cases, we're looking at heat entering the water. So that kind of changes the sign. So you need to change the order of the temperatures in here. But if that's maybe a bit confusing, it has to be positive in this case. If you don't want to have to worry about getting all these signs right, we know this has to be, both of these have to be positive. So the initial temperature of the rock is bigger than the final temperature. So this first line is positive. However, the temperature of the water water starts off cooler. So the second line is also positive. So that's a quick check. They both need to be positive in this case. Now, these are both equal to each other. So we have mass of the rock times the heat capacity of the rock minus final temperature equals mass of the water, heat capacity of the water, final temperature of the water minus initial temperature of the water. So these are equal. Now, there is a fair amount of algebra we need to do, because what we want is we want an expression that tells us the final temperature. So let's start by expanding all the brackets. There are quicker ways to do this, but I'm going to do every step. Now, let's move this to this side and then move this to this side. So we have CR. I want to put the brackets here. So both of these terms have a TF in them. Okay, so now we've calculated, so we've got the TF on one side. So we're going to divide by this. And we end up with TF equals MRCR plus WCW TW So we've got this final expression. Now, the last thing we need to do is plug numbers in. So what have we got? We've got, so the masses, well, notice firstly that the masses were given in grams and milliliters. So mass of the rock is equal to 350 grams, equal to 0.35 kilograms, and the mass of water is 600 grams. So 1 milliliter of water weighs 1 gram. And then 600 grams, which is 0.6 kilograms. We're told the temperatures, but we're told the temperatures in, I'll use a different color, Celsius. We need to get them into Kelvin. So we have temperature of the rock is 45 degrees Celsius, which is equal to 45 plus 273 Kelvin, which is 318 Kelvin. And the temperature, the initial temperature of the water was 4 degrees. Which, excuse me, we need to convert into Kelvin again. So we add 273. So we end up with 277 Kelvin. And now we're in a capacity, we're in the position, we can just plug these numbers in and we get the final temperature is 0.35 times 700 times 318 Kelvin plus 0.6 kilograms times 4,200, which is the heat capacity of water, times 277 Kelvin, divided by 0.6, the mass of the water, times the heat capacity of the water, plus 0.35 kilograms times 700, so the heat capacity of the rock. If you plug that into your calculator, you get 281 Kelvin, which is equal to 8 degrees Celsius, which makes sense. The rock, both rock and the water end up at a temperature kind of in the middle of the two, except it's much closer to the water temperature because A, there's more water to absorb the heat, and also it has a higher heat capacity. So it absorbs more energy without changing temperature very much. Whereas the rock changes its temperature quite quickly as it loses energy. Okay. Are there any questions about that? That was maybe quite an involved question. Okay. So in the next section, we're looking at ideal gases. So most gases can be approximated as an ideal gas, but the kind of formal approximations are the particles are point-like. And what this really means is, because nothing, it's not really an actual point. What this means is the distance the particles travel between collisions is much, much greater than the size of the particle. So in other words, we can just ignore the particle's size. And we also have that the only interactions they have is scattering off each other, bouncing off each other. So there's no kind of electromagnetic force between them. There's kind of no other forces between them. They just don't interact, hit each other, and then stop interacting again. The only thing they interact is when they hit each other. The classic example is like kind of billiard balls. Okay. Now, in your sheets, you're given loads of different equations that all apply to an ideal gas in different settings. But, and I think you show it in the sheet, you can put all of these together to make the ideal gas law. There's one big equation, it's not that big, which says that the pressure of the gas times the volume of the gas is equal to N, which is the number of moles, R times the temperature. So we've got pressure, volume, moles. Here, this is called the ideal gas constant. And it's equal to 8.3 joules per Kelvin per mole. And here is the temperature. And as always, temperature is in Kelvin. Now, moles is, I think, always a bit, is useful. It kind of makes numbers nice, but to get your head around it, 1 mole is just 10 to the 26 particles. So 10 to the 23 particles. And so we can rewrite this in terms of n here, which is the number of molecules or particles times this other constant, Kb, times temperature again, where Kb is called Boltzmann's constant, and it's equal to 1.38 times 10 to the minus 23 joules per Kelvin. We'll see that N times R is equal to big N times Kb. They're just different ways of writing the same equation. If you want to do it in terms of moles, but moles just counts particles. So you can rewrite it in terms of the actual number of particles times this other constant, Boltzmann's constant. I mean, I personally prefer the second way. I think it's more physical. You're just counting molecules, but it does mean you have N is usually huge, and then this Boltzmann constant is tiny. So you end up with really big and really small numbers, which I guess a lot of people don't really like. So it's up to you. It really doesn't matter which way around you do it. So let's have a look at a problem. So a laboratory vacuum can have a pressure that's 10 to the minus 13 pascals. How many molecules, we're going to use the one with big N, are there per cubic centimeter for such a vacuum at room temperature? Okay, so we have the pressure is equal to 10 to the minus 13 pascals. The temperature, room temperature, is 20 degrees Celsius, which is equal to 293 Kelvin. In fact, what you'll see some people do, if they're just doing a very quick calculation, they'll say room temperature is 300 Kelvin. It just makes all the numbers nicer. And really, the difference between 20 and 27 degrees may feel a lot to us. But actually, in lots of these equations, it really doesn't change the answer. And if you just want a quick estimate, 300 Kelvin often works. And the volume, now the volume is 1 centimeter cubed. And 1 centimeter is 0.01 meters. So it's going to be 0.01 cubed times meter cubed, which is 10 to the minus 6 meter cubed. So now we use the ideal gas law. So we have PV equals big N Kb T. And this we can rearrange to get big N equals PV over Kb T. So the pressure we said was 10 to the minus 13. The volume was 10 to the minus 6. The Boltzmann constant was 1.38 times 10 to the minus 23. And the temperature was 293 Kelvin. And if you put this into your calculator, and if I've done it correctly, we should end up with 25 molecules. in this little centimetre cubed of volume. Okay. Okay, this next question is quite long, but we'll do it step by step. So, eventually we're going to see how much force is needed to open a freezer door. So, before the freezer is turned on, what is the mass of the air inside? So, what we're going to do is we're going to work out the number of moles. So, step one, we're going to work out the number of moles inside. And then we're going to work out the fact that it's 28 grams per mole. So, step two is use the molar mass. And this is at room temperature. So, before the freezer is turned on, we're at room temperature. So we're at, which we've just said is T equals 293 Kelvin. So using the ideal gas law, this time we're going to want moles. We're going to have nRT. This, if we divide by RT, gives us the number of moles was pressure times volume divided by RT. Now, pressure, standard air pressure is 10 to the 5 pascals. That may seem like a lot to have 10 to the 5 newtons on every meter of you. But the reason we don't feel it is because there's air inside us pushing out. It's a surprisingly large number, I always think, atmospheric pressure. So we have pressure is 10 to the 5 times the volume. Now the volume is 1 times a half times a half. Or 0.5 times 0.5 divided by R, which was 8.31, and then times 293. And at the end of this, we get 10.3 moles. So that's the number of moles in the fridge, in the freezer. So the mass is equal to 28 grams per mole, which is from the question here, it's highlighted, times the number of moles, which gets us 288 grams or 0.288 kilograms. So this is the mass inside a fridge. So the next question is, how long does it take a freezer to cool down to minus 18 degrees, which is the temperature a freezer kind of normally operates at, I think. So we're told the power and the efficiency. So let's start off, before we look at that, let's work out heat needed, or the amount of heat needed to take out of the fridge, to extract from the air inside the freezer. So the heat extracted, go back to our specific heat formula equation, specific heat capacity equation rather. So the heat is equal to the mass times the specific heat capacity times the change in temperature. Now, we're told that the specific heat capacity is 720. So we're told C equals 720 joules per Kelvin per kilogram. We've just worked out the mass. I don't know why I'm using all these different colors. we've just worked out the mass is 0.288 kilograms. And finally, the temperature difference is we started off at 20 degrees. And if we're looking at temperature differences, we can use Celsius or Kelvin because the differences are the same. We started off at 20 degrees and we finished at minus 18 degrees. So we have 38 degrees. And because it's a difference, it doesn't matter whether we use Celsius or Kelvin. So we put all of these numbers in. So we have 0.288 times 720 times 38. And this gives us 7,880 joules. So this is the amount of energy we need to extract from the freezer. So we're given the power and the efficiency. So if it's got a power of 100%, the 25% of that is wasted. The effective power, that's the power that's actually being used to extract heat, so the useful power, this is equal to 0.75 times 100. This is 75% times the 100 watts, to 75 watts. So in order to get the time, we know that power equals energy divided by time, which means the time is equal to energy divided by power, which is equal to 7,880 joules divided by 75 watts, because we're looking at the useful power. And this gives us 105 seconds, which is a bit less than 2 minutes, which seems a bit quick, really. Our freezer doesn't cool down that quickly. I mean, if you think of all the reasons why, I would say this is actually, firstly, quite a small freezer. Secondly, a freezer will get less efficient as it gets colder. It's at the same temperature, it's much easier to extract heat. As the freezer gets colder and colder, it gets much, much harder to extract it. So the efficiency goes down. If a freezer's got stuff in it, like frozen peas or whatever, we've already seen that, well, they're made of water. We've already seen that water has a really high specific heat capacity. So actually, you'd need to remove a lot more heat in order to cool it down if there's things in the freezer. So this is very much a lower band. So what was question C? What is the pressure on the door inside and outside? So outside, the pressure is 10 to the 5 pascals. It's just 1 atmosphere. Nothing's changed about outside. Inside, we're going to need to use the ideal gas law. So we have PV was nRT. So the pressure is equal to nRT over V, which we've already worked out the amount of moles back in part A, which was 10.3. R is equal to 8.31 joules per Kelvin per mole. The temperature inside is minus 18. So that gives us 255 Kelvin. So again, we've gone 273 minus 18 to get from Celsius to Kelvin. And we divide that by the volume, which is 1 times 0.5 times 0.5. And what I've just noticed in my notes is I put 2 5, so I'll use a calculator and do it again. But we have 8.7 times 10 to the 4 pascals. So the pressure difference is quite a lot. So finally, well, this takes us on to D. If the freezer handle is at the edge of the door, how much force do you need to open the freezer? And now we know that opening a freezer is sometimes quite difficult. That you have to really overcome all that pressure from the outside. So now we're going to calculate that. So the pressure difference, well, let's draw a diagram. So we have our freezer with our door here, with its handle. Here we've got low pressure and here we've got high pressure. So this pushes in and this pushes out. And then when you're pulling here. And what we want is, in order to open the door, the moment from the pull overcomes the moment of the pressure pushing the door shut. So let's have a look. So to calculate the pressure, let's just look at the pressure difference. So the pressure difference this is 10 to the 5, take away 8.7 times 10 to the 4 equal to 1.3 times 10 to the 4 pascals. Now, we could be really complicated. If we're trying to work out the moment we could be really complicated and we could go along each part of the door and work out the moment on each little strip of the door. However, if the force acts evenly over the surface, when you're calculating a moment, it acts from the center. So the total pressure, it acts from the center. So when we're counting moments, it acts from the center. So the total force from this pressure is the 0.3 times 10 to the 4, so that's the pressure, times the area, so 1 times 0.5. Remember, it was 1 meter high and a ½ meter wide. The other 0.5 was for the depth. And this gives us 6,500 newtons. Now, the moment here just said, because the force is evenly distributed, it acts as if it's in the center. So rather than working out the force everywhere, we just say the moment from the pressure is the force, 6,500, times the distance. Now, this distance here, 0.25 meters. And this gives us 1,625 Newton meters. Now, the moment from our hand, from our pulling, this is the force of us pulling times the distance, which is half a meter. And we know that this must equal this in order to open the door. Okay, so the force is equal to 1,625 divided by 0.5, which is 3,250 newtons. Which is remarkable and clearly wrong. So you clearly don't have to put in 3,000 newtons of force to open a freezer. So let's think of some reasons why this might be. So there's going to be leaking in the freezer. So as it cools down, because of this massive pressure difference, air is going to seep into the freezer. And because of that, the pressure is actually going to be quite equalized. The freezer's a bit lower pressure, so you need a bit of force to open it. But air goes in as you freeze it. In fact, that kind of has to happen. If that didn't happen, you'd put in your bag of frozen peas. You put something in and it would be hotter than the air inside. So it would be a much higher pressure. You'd put your frozen peas in, shut the door, and it would explode because the air in the bag hasn't had time to cool down. So it'll be at the same pressure as outside. You put it into the freezer, which is at a much lower pressure, everything would explode. And that doesn't happen. So clearly there's quite a lot of leakage that makes the pressures inside and outside the freezer equal, or at least much more equal than what we've calculated here. All right. Are there any questions at this point? Okay. Okay, then the final section for today is kinetic theory. So I said right at the beginning that temperature is to do with the amount of energy in a substance. And that is explained by the equipartition theorem. And this says the average energy per degree of freedom is a half times the Boltzmann constant times the temperature. So this tells us, so let's think, if we just have a single atom, then it has 3 degrees of freedom. It can move up and down, it can move left and right, and it can move forwards and backwards. And so as you increase the temperature, it moves around faster and its energy increases, as it says here. If you have a more complicated molecule, say, we'll see this in the next question, something that's like oxygen, so it's got 2 atoms in it, D of E stands for degree of freedom. So a degree of freedom is the ways something can move. And so, yeah, like helium, which is just a single atom, all it can do is move. So it has 3 degrees of freedom: up, down, left, right, forwards, back, forward, back. And as we'll see, something like oxygen has 2 atoms on it, so it can move. The whole thing can move in 3 directions: up, down, left, right, forwards, back. It could also vibrate, which is another degree of freedom, and it can also rotate in 2 directions. So if here's our oxygen molecule, it can rotate like this, in this direction. It can rotate in this direction. But we've already said that these atoms are point-like, and so it can't rotate this way. And you probably can't even see me rotating it on the camera, because if this is so thin and it's just a circle, it doesn't, rotating it in this direction does nothing. So there's no degree of freedom in this direction. And so oxygen has 6 degrees of freedom: 3 for the movement of the whole thing, 1 for vibrating. I'll have to take the lid off to do that, and then 2 rotational, which makes sense. It's got 2 molecules. So let's have a look at the question. I've preempted a little bit here, but oh well. We can look at it in more detail then. So we want to compare the average thermal energy in 1 mole the gas of a diatomic molecule. So that diatomic means 2 atoms. I'm highlighting everything. Diatomic means 2 atoms. So as I've said, oxygen, and compare that with the thermal energy contained in a gas of a monatomic gas. So this means 1 atom. So let's consider oxygen for starters. We've said as a molecule that's got 2 atoms in it. So it can move up, down, can move left, right, and it can move, I'll try and draw this. That's meant to be an arrow. There we go. Is that, yeah, up, down, left, right, and forward, back. So it has 3 translational, or just move. Then it has rotational, so it can spin in that up-down direction, and it can spin like this. So it has 2 rotational degrees of freedom. Then lastly, it can go and vibrate. So it has 1 vibrational. So overall, this has 6 degrees of freedom. So this means each molecule has 6/2 kBT joules of energy. And then argon, this is just a singular atom. So all we can do is move around. So it has 3 translational. But it's just a point, so it doesn't rotate, it doesn't vibrate. Yeah, all it can do is move around. So it has 3/2 kBt of energy. This is all per individual molecule. Now, the question asked for 1 mole, not 1 molecule. So the energy per mole equals Avogadro's number, which is the amount of molecules in a mole, times energy per molecule. So let's look at oxygen first and calculate the energy in a mole of oxygen. This is equal to 6/2 kBt times the number of molecules in a mole. Here, though, we have the quantity Kb times Na. Go right back up to the last section. We see that N times Kb, the number of molecules times Kb, gives us the number of moles times the ideal gas constant. So, if there's Na molecules, there's only 1 mole. So we can rewrite this, where are we? Down here, as 6/2 times R times T, and then the energy, the argon, is equal to 3/2. I'm going to do the same trick again and write it as RT. And now as a quick estimate, to try and put numbers on this, we get a feel of it. We're going to say T is approximately equal to 300 Kelvin. It's a bit more than room temperature, but as we said, for an estimate, it's good enough. So this gives us 7,200 joules, and this gives us 3,600 joules. So the oxygen has double the amount of energy in it. Are there any questions about the equipartition theorem? I mean, the equipartition theorem underpins a lot of kind of our understanding of how materials work. So from here, we can see that if we increase the temperature, for a given temperature, oxygen has twice the amount of energy as argon. And this means that things like the heat capacity of oxygen will be twice that of argon, because oxygen has so many degrees of freedom. So the more degrees of freedom something has, the higher the heat capacity. And kind of these kind of things underpin a lot of material science. So, on to the last question. I think we're going to finish a bit early. Let's have a look. So the inside of a light bulb contains noble gases. And the reason for this is that they're inert. So you may remember from GCSE chemistry that group 8 or group 0, they don't interact. So they're really good for light bulbs. If you had oxygen in a light bulb, not only would it might burst into flames, but it would rust really quickly. As that filament heated up, it would react with the oxygen and rust instantly. You don't want that. So lights always contain things like argon, neon. For most ordinary lamps, it's in your house, I think it's argon, although everything's become kind of, lights aren't built the way they used to be. So it may have changed. But either way, a crack appears in the glass such that the gas leaks out. What is the ratio of the leak gases? So in other words, how many molecules of one leak out compared to the amount of molecules of the other? So let's have a look for starters. Let's say we have our light bulb. And there's a little crack. I can't, this is a terrible drawing. About here. And let's say in a little bit of time, the gas is all moving around. Let's say, for now, argon has speed v argon, and neon has speed, velocity v neon. Now, in 1 second, argon, any argon that's in this region here, well, this length here is time times v argon, can escape, roughly. It's not going to be exactly a rectangle, it's going to kind of spread out a bit. And so not everything escapes, not everything's going in the right direction. But as a ratio, we can just look at the size of this. So everything in here has a chance of escaping. And everything in here for neon has a chance of escaping. So in other words, the faster the molecules can move in a given time, more of them can escape. So we need to work out the speed of the two molecules. Now, what we also want is we don't care about the speed in the up-down direction or the forwards-back direction. We just care about the left-right direction. So let's call this x. Doesn't really matter. Let's just call it x for now. The reason is, on average, we said each degree of freedom, and a degree of freedom is something it can move as, so it can move in the x direction. So moving in the x direction is 1 degree of freedom. So this has a half kBt of energy, and it's moving, so it's all as kinetic energy. So half mvx squared. We just said that moving in the x direction is 1 degree of freedom. They have others, but moving in the x is just one of them. So this gives us Vx squared equals kBt divided by m. And this is the mass of the molecule. So the velocity is equal to the square root of kBt over m. And we've already said that the amount that can escape is proportional to the size of this region I drew. So the amount that can escape is proportional to the x velocity. So if we want to look at the ratio of the number of argon that escape versus the number of neon that escape, this is going to be equal to the x velocity of argon divided by the x velocity of neon, which, put in, C over M of neon, which becomes square root, and we have mass of neon by the mass of argon. Okay, here we'll remember that these are mass per molecule. And what are we given in the question? We're given mass per mole. So M of neon is equal to the mass for 1 mole of neon, which is given by this mu, which neon divided by Avogadro's number. So divided by the amount of atoms in a mole. So saying is, yeah, okay. Similarly for argon, equal to mu of argon divided by Avogadro's number. So if we put both of these into here, we have square root of mu neon divided by Na, mu of argon divided by Na, and these Avogadro's numbers, they cancel. We have the square root of mu neon over mu argon. And if we have a look, this is the square root 20 over 40, which simplifies to the 1 over the square root of 2. Okay, that's the last question I have planned for today. Are there any questions from your side? Or anything you want me to go through, or? Okay, if not, I'll see you all in a week's time. Yeah, in a week's time. And when we do that, we'll be looking at the first laws, kind of thermodynamic cycles, so how engines work and how energy flows through engines. Then, yeah, that was your last session, I think. Last.
Yes, this is going to be the last session for year 13. Thank you very much. Thank you very much, Toby.
It's okay.
All right, I'll see you next week then.
Okay. Bye-bye.
Okay. Bye.